Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you guys are doing good. In this, we're going to see problem number 3202 and 3201. Both are same. It's just a small difference. But before that, this is the third and the second problem of today's contest. Fourth is already live. And I think that this one is going to be longer and a bit trickier than that one. And again, for the folks who are just worried about its top-down solution, keep watching. Cool. Let's see. It simply says that you are given an integer array nums and a subsequence of nums. They have called the subsequence as sub of nums with the length x is called valid if it follows this condition. Now, considering that you have this nums and subsequences, you choose some random numbers in the sequence. That is called as a subsequence. So these white ones, when they are represented as form of an array, it is called as one subsequence. Now the condition which they have given is that if I take the subsequence in a new array, then subsequence of 0, subsequence of 1 on adding modulus with 2. Again, the only difference between this problem 3201 and 3202 is the modulus. Here the modulus is with 2, here the modulus is with k. That's it, only change. Now coming on back, we have to do is subsequence, take consecutive sum, modulus by 2, consecutive sum. Again, this is subsequence of like the sub of 0, sub of 1 mod by 2, then sub of 1, sub of 2 mod by 2, then sub of 2, sub of 3 mod by 2. Cool. Okay. Then if I just apply a simple math operation, if I try to evaluate this, it will come down to be that sub of 0 mod 2 plus sub of 1 mod 2, it should be equal to sub of 1 mod 2 plus sub of 2 mod 2. It should be equal to sub of 2 mod 2 plus sub of 3 mod 2. Now, in this case, I can simply cut this down. So ideally, sub of 0 mod 2 should be equal to sub of 2 mod 2. Or if I also say that if I compare these two, then I can cut these two down. Then sub of 1 mod 2 should be equal to sub of 3 mod 2. Okay, so this is a condition which we have received. Again, this sequence will keep on going. Now, with this condition, what we have figured out is that I want some kind of a subsequence. I want some subsequence which should have one element remaining in between, which should have one, because see, it says sub of 0, sub of 2, which means sub of 1 is remaining in between. So that's one thing. Now I want some subsequence which should have one element in between, and the modulus of these which I am taking, alternate ones, should be same. There's a small catch. Although the modulus of these one should be same, but these one also should be same. That is represented by this one. So ultimately we realize that ultimately I am doing mod with what? I'm doing mod with 2. So this modulus operation ultimately can be a 0 or a 1. It can be a 0 or a 1. It can be a 0 or a 1. So the first thought or the first intuition comes to our mind is that it can be either a 0 or a 1. If that's the case, first ask us to build a subsequence, then verify that subsequence is valid or not. Then I'm good to go. So building a subsequence will take to n time. Then validating that will take another n time. So it will be this much time complexity, which will for sure give us TLE. Now, because at every index I have two options, either I can put a 0 or a 1, then I will be able to form some subsequence. Okay, but still, what my task was, maqsad was, prime aim was to maximize the subsequence length, and this maximization will take place considering I go on to any random index. I will have to look for the previous index. Depending upon this, let's say I am standing at this index I will look for the previous index having again, it can be either same, considering you have considered one gap in between. So we realize that I'm at an index, I will have to look for something backwards which should be same. If it is same, then I should have one gap in between which should incorporate some different element or also same. That was a bit hazy, right? Let's see. So we realize ultimately our mod operation can be a 0 or a 1. So far we realize it's a subsequence, and maybe I have to I have to maximize my length of this subsequence. valid subsequence. So I realized it can maybe I have to memorize something. How? Let's see. So I have a 0. In this, I realized that if I'm standing at this specific index, I will take the previous 0 because I want to make things same. I want to make things same, but also I should have something in between. Same way, I could have a 1 here. I need to make things same, and I should have something in between. Now that something, it can be a 0 also, it can be a 1 also. It can be a 0 also, it can be a 1 also. So ultimately, you will see that you found out these cases. Either it can be a 0, 0, 0, all zeros, or it can be alternating 0, 1, 0, 1, 0, 1 like this, or it can be all like it can be alternating again, but 1, 0, 1, 0, 1, 0 like this, or it can be all ones. So these are the only cases which will give you a good subsequence. So either you can separately solve for these cases, also you will be good to go. Now, because of what we have already seen that we had two options, either place a 0 or 1, and thus we know that how 0 and 1 need to be placed. Either they can place all consecutively, or they will be placed alternatively. Thus we realized we have two options, place a 0, 1, and placing pattern is also known to us that either consecutive or alternate. Thus I can simply memorize it, and it will be similar as that of LIS. If you don't know what LIS is, go and watch this video. You will get how these kind of problems are interpreted as a DP problems. I hope so. If you are watching us so far, you would have realized it's actually a DP problem, and you would also realize that okay, I can memorize something, but comes the tricky part. How you will do it is the prime thing. Now we realize one thing for sure, that if I'm standing on any specific index I, right, my previous thing, ultimately I'm not concerned about the indexes as such, I'm concerned about the parity, because everything you saw here was on the subsequence, but you are given the actual nums array which will have indexes I, for which you will have to find the opposite or the same parity. Thus we realized that if I'm standing on some specific index, I will find the current remainder. Current remainder saying current parity. Why I am saying current remainder and not parity is because future you will go to remainders, because right now you only have 0 and 1. So you can say okay, parity. But then when the remainders will be more 0, 1, 2, 3, then you have to find the current remainders only, right? That's the reason I'm standing at the index I, so I have the current remainder as nums of I mod 2. Okay. Now because of this nums of I mod 2, which means at this index I will look for what? Either I can look for a different parity. So if I'm standing at 1, I will look for a 0. I will look for a 0. So I will, like you can say that different parity. You are standing at 1. Again, different parity says, I'll tell you what it says. Different parity, you are standing at 1. Then maximize the length. Your basically difference is, you can imagine this as a DP only. So this difference is the DP only for you. Difference of current remainder, which is 1 right now. Maximize that ending at that specific remainder, ending at that specific parity of 1. Go and check the previous parity again, because I am saying it is a different parity, which means I am following a pattern of different parity, which means the previous parity should be a 0. So same way, go and ask your different parity DP only, but for a 0 value. Now I will say up till this point 0, what is the maximum length? Up till this point 0, what is the maximum length? Add a +1. Thus you will get for different parity ending at 1, what is the maximum length? Now you will say, Aryan, okay, makes sense, but then why is this different needed? Like, can't you just put a DP here? Your question is right, but let's see what if the parity is same. If let's say again, you could be placing a 1, but now you are saying the parity, you are continuing the same parity, which means right now my current remainder is 1 and I'm continuing the same parity. So I'm using a same DP. Again, you can imagine this as a same DP. Now this will tell me, same DP will tell me, okay, continuing the same parity, I have to maximize my length. Again, maximizing the length, previous number should also be same. Here you saw, I flipped. If I had a 1, I made it a 0. If I had a 0, I would have made it a 1 to find for the previous number or a previous remainder, I should say. But here in this case, I'm looking for the same number. So if it's my current remainder, I will look for current remainder only, which is my previous remainder. It should be same. It should be, as you can see, this one is actually this one only. It should be same. Thus, I'm maximizing my length. Now, okay, you will say, Aryan, makes sense, but what I thought of in the contest was that I will put a DP here. Okay, DP here, DP here, then again DP here. You see a very big issue because this DP was for different parity. It should keep on alternating. This DP was for the same parity, but if you miss or if you mix both of them, then what will start happening is, for a 1 you will look for a 0, but you should look for a 0 which should have also followed different parity previously. But because of you have mixed, there is a possibility that you will be picking a 0 which was following the same parity. So just for the behavior of maximizing your length, you would have done 0 0, which means same parity, then different parity, then different parity, and then same parity. So which is incorrect. So you will have to separate out two things, which is different parity and same parity. You have to separate out. So we realize the code will look something like this, that I will go on to all the indexes. For every index, I will have the current remainder. For the current remainder, I will look for the same parity. For the same parity, again, if you look at this code's example code, so you're just adding 1 in the existing number itself. So it will for sure be higher than the number itself. So I've simply assigned my same of current remainder to 1 plus current remainder, 1 plus same of current remainder. So you will see same parity, I can just increase the length by +1. For a different parity, I'll say, okay, if the current remainder is 1, go and look for different parity ending at a current remainder, ending at the remainder of 0. If it is 1, it will be 0. If it is 0, it will be 1. So I'm looking for a different, I'm looking for an opposite parity, but my sequence should also be different. As in, when I say different, it means 0 1 0, alternating. Thus, whichever is giving me maximum answer. So this same can, again, as I showed you, I will have 4 options. Same parity ending at 0, different parity ending at 0, different parity ending at 1, different parity ending at, same parity ending at 1. So out of all of them, same parity ending at 0, same parity ending at 1, different parity ending at 0, different parity ending at 1, whatsoever is giving me maximum length, that is going to be my answer. You can see simply that the time complexity for this will be O of n, and the space will be, as you can see, I have only used vectors of size 2 to 2, so space will be O of 1 only. Now, although your question 1 is done, but the other way to write the same problem or to think of the same problem is that, as you saw above only, that for any, why you needed this same and different. Why? The prime reason why you needed that was because that for a specific number 1, as in the specific parity 1, you were looking for what? You were looking for any parity, other parity. Let's say you were looking for a 0, but then it should also have followed a 0 1 kind of phenomena. If I go back and show you example, if I have a 0 1 0 1 1 0 1 0, example this. So for 1, if you're looking for a opposite parity 0, then the sequence, how the sequence will look like before the 0 will be another 1, then another 0, then another 1, then another 0. So because of the fashion of the problem, which is this, it ultimately says if the final subsequence is in this order, so these should be same and these should be same. These again, these should be same and these should be same. If that is the case, if that is the case, we realized if the current remainder, I'm looking for some previous remainder, then before this previous remainder 0, I should be making a sequence same as that of the 1, which means that before this 0, I should make which should have a back as 1, which should have back as 1. So if this is my current remainder, this is my previous remainder. Before this previous remainder, again, before this previous remainder, which means previous of this previous remainder should be equal to my current remainder. Make sense? Make sense? That is what I needed. That if I am at a specific, if I am at a specific current remainder, I'm looking for some previous remainder. His previous should be equal to the current remainder. That kind of previous I can take in. Aryan, what do you mean by that kind of previous? Which means that this previous remainder 0, it could also had a previous of this 0, which will make him same parity. This current 0, it can have a previous 0 as 1, which could have made him different parity. So I am saying that if I am at a current remainder 1, I should, and if I'm going on to my previous remainder as 0, then this 0 should have come from a previous remainder as that of 1 only, which is same as that of current remainder. Which means if I change it to 0 in future, then if I'm looking for a 0 only, which means I'm looking for a same parity, which means this 0 should have occurred previously, which means I should take this as the current remainder. For this previous remainder, his previous should be this one of the same parity as that of 0. So ultimately, if you still don't understand, no worries, I'll explain you much more further later on, but this is the same, we can interpret the same problem. Thus, I realized that I can write the same thing as for the current remainder with the previous parity as 0. I have to maximize the length, but maximize the length by saying the thing which you're taking, the current parity is 0 with the previous parity as that of current remainder. So I looked for in this portion and said the current, I'm looking for something whose current, because right now he said that I am standing here, I'm looking for something having the parity as 0 previous. So for me, the previous parity should be 0. So for this current, the previous parity should be, let's say, 0. Then this portion will go and ask that for me, I am 0, my current parity is 0, and I'm looking for a previous parity of 1 only. 1 only. I'm looking for the previous parity. So I'm looking for, I am 0, I'm looking for a previous parity of current remainder only. Same way, if my current remainder is here and the previous parity is 1, then imagine that you are at 1 and you're looking for a previous parity of current remainder only, and thus adding a plus 1, which means that if I am at 1 and I looked for a 0, so I will ask my DP, I'll ask my DP of 0 and the current remainder only, which means 1, which means this one. So whatsoever is the answer for this, which means DP of 0 and 1, this represents current remainder, this represents previous parity, and only that I can attach it to my current remainder. Thus, I will simply, because this is a new attachment, so plus 1 for this attachment. So plus 1 for that attachment. Just maximizing the length. This is another way to solve the same problem. Thus, we realize the code will look exactly same as what we saw. It's just that now I need current remainder and my previous remainder. Current remainder also can be a 0 or a 1. Previous remainder are actually 0 and a 1. So I need to make a vector of size 2, 2. For this current remainder 0, 1, and the previous remainder 0, 1. Now exact same code. Current remainder is nums of I mod 2. My actual snippet, it says current remainder looking for a previous parity of 0. It should go and say if the current parity of me is 0, I should look for the previous parity of as that of same as that of current remainder. Same way for 1. Ultimately, maximize your answer, maximize your final length. Ultimately, you will get the final length. Again, same time complexity and same thing, same space, which is O of 1. Again, I have showed you it's O of k square, because as we go on further, because we know the k will change, the k will actually be k, which is this problem in which the k is there instead of 2. Exact same thing. It's just that rather than now checking for a previous parity as only 0 or a 1, now I can have a previous parity as anything. And when I say anything, it can be 0 to k minus 1 because I am doing a mod with k. So for sure, my previous parity I need to look for from 0 to k minus 1. So if my current parity, or I can say my current remainder, let's say is nums of I mod k. So I will try to look for all the previous remainder from 0 to k minus 1. Same way, which means that for this current remainder, if I'm looking for some specific previous remainder, I can only take the influence, which means I can only take the dp of this previous remainder, which had its previous same as that of current remainder, which had its previous, again, this next portion is previous, which had its previous, sorry, when I say this next portion, as in like my dp next state, which had its previous as current remainder. So exact same code, that dp of current remainder when the previous remainder is this one, I should maximize my answer. So take exactly same as it is. Then 1 plus, go and look for this previous remainder as the current value, whose previous value should be same as that of my current remainder. If I am finding answer for this I, so it should be same as that of my dp of previous remainder comma current remainder. Exact same code as what we wrote just above. So the code will look like exactly same. I'll show you code quickly. Firstly, the code, as you can see, will look like exactly same. I made the exact same dp array, exact same current remainder. It's just that I have to try for all the previous remainders now. I cannot hard code 0 and 1. I have to try for all the previous remainders. I'll try for all the previous remainders and thus maximize my answer by 1 plus dp of previous remainder as the current value, whose previous should be equal to the current remainder, and ultimately maximize your answer. Same exact same code, maximize your answer and ultimately return the answer itself. As you can simply see, the time complexity for this is O of n into k, and the space because of this will be O of k square. For the folks who want a quick dry run, for them I've done a quick dry run, although it's not required. But yeah, as you can see in this case, my dp of 1, previous can be either a 0, 1 or a 2. These are previous remainders. I have to maximize my answers. I have not written that max equals to maximize this comma this. I have not written that, but you know that you have to maximize your dp values. Then 1 plus dp of 0 and 1, which means that I was saying right now I am standing at a remainder value of 1. I'm looking for a remainder value of 0, but he will say you should look for a remainder value of 0 whose previous is a remainder of 1. So as you can see in the very beginning, there is no 0 whose previous is 1, so the value is 0. So I got the length as 1 so far, which means the length of the element ending at 1 whose previous is 0 is of the length of 1. And as you can see, you can just go through it, dry run it. I've like done for you guys. It is exactly same. I have done it for all these steps, and thus I will get the final answer as 4. Again, the last one will actually optimize and finally give you a value of 4 by taking any of these, you can say. Now with this, you have got that how this is done. But many of you have a question, Aryan, always show us the top-down approach first. But firstly, the worst you can do is start thinking about top-down approaches for simple linear DP. In the actual courses also, I have told earlier that not necessarily you have to think of top-down every time. For example, in this problem, thinking of top-down, okay, would have helped you. But how much? That would have been a case. Because here you just have to look for a previous parity of 0 or a 1. Okay, no worries. But still, we saw that we have to look for just a previous parity, and it can be either a 0 or a 1. So we just went about making the variable only. Now, in this problem, if let's say you would have asked Aryan, now in this problem where the n and k is there, I want to go and look for the actual top-down approach. If you go about and think in a top-down approach, firstly, if you were to think in top-down approach, you would need index. So if I'm at specific index, I need to look for what? Some previous index. I will look for previous index. Then I can choose the previous index, that specific DP value whose previous has the same parity as this current remainder. So if I say this current index I has a current remainder of current remainder, then I can look for some previous index j whose parity should be same as that of current remainder. So for every index, I will have to maintain the index along with the previous parity, or you can say previous remainder. I have to maintain that for every index. But if I am at a specific index, I will have to look for all the previous either parities or the indexes. So which will say that for the current index, you will go and look for the previous index. For the previous index, you will take a dp value. You will take a dp value whose parity is same as that of current index, which again, as can roughly see, it will take O of n square into k. But you can see that this previous index, previous remainder will be same as that of current index. So it can change to O of n square. In this example, O of n and k both are same, thus it will work. But still, I'll highly recommend that if the n would have been high, then this would have caused a bit problem, which means that in this case you'll see Rn n and then k you are also going, so it will be roughly n into k. Yeah, 5 into 3 will bottom, like in the little rough estimate, will actually be passing. But if it would have been 1/4, then your n square approach would have failed. But for top down approach, you will have to need to have a n in that case, which means in best case I can optimize it to O of n square. That's it. In top down, you cannot optimize this code to O of k square, like O of n into k or O of k square. You will see that you can do it in O of k square also, but okay, like sorry, not O of k square, but O of n into k. Okay, so that again, if you're wondering, it's a simple code of top down that you are at a specific index I, current index I, you will go and look for all the previous indexes j, and you will say that I am a current index I. So I look for all the previous indexes j. Let's say int j is equals to something, that okay, j is, let's say 0 to j is less than I and j plus plus. Then look for the previous index and say again the current parity, which means the current remainder is actually equal to, tell me, it's equal to nums of I mod k. The previous remainder will be equal to nums of j mod k. Now, in this case, when nums of j mod k is there, you will have to go and look for your dp value of starting from j, but having the previous remainder as current remainder. So in your code, you will have to store your dp of I comma current, or dp of I comma your current remainder. As in, like, you will have to go and try for all the possible previous remainders, which means this previous remainder. So you will store dp of I comma previous remainder is actually maximizing your answer, again maximizing your answer, which means this dp of I comma previous remainder, then comma 1 plus this value dp of j comma current remainder. Thus you realize that you would ultimately need to keep track of your I and your previous remainder, but making a complexity down to O of n square, but your space will be again O of n into k. So this, where's the code gone? Yeah, this will be your again, in this case you saw for top down, the time will be O of n square, n into n, but the space will be O of n into k. For bottom up, which we have seen right now, will be O of n into k, because O of n into k, and the space will be O of k square. Cool. Again, the code is exactly this only, that just memorize it. If I is equals to n, then simply return a zero, and if my dp of I comma my previous, or my, let's say, some remainder, I will from my main function I will call the specific thing for all the previous remainders, which means I will call for the previous, for this is from my main function. I will call this entire stuff for previous is equals to 0 when previous is less than k, and then previous plus plus call for the solve function from starting from the index 0 with this previous value. So I can simply here only say that if the specific dp of I comma previous, if it's not equal to -1, simply return that dp of I comma previous thing, I comma previous thing, dp of I comma previous thing. Now when this portion is done, you will simply go on to this for loop, try for all the previous indexes, in which you will simply go on to all the previous indexes and then simply return your answer back. Now you can simply return let's erase this, simply return your dp of I with that specific previous like remainder, which you will always keep on maximizing here itself. I guess if it is maximizing, so I have to make a variable, let's say answer or something, which will maximize and then assign that answer here, so that in my main function I can initialize my dp value with the -1, dp of I comma previous remainder as -1, like initialized to -1 as in the entire n and for entire k. Cool. Now coming on back, we diverted a lot just for the top down, but again the emphasis was that try to think both in terms of easiness and in terms of how easy it is to look at a specific state. Top down is always not an easy approach. Cool. Coming on back, the question was, can you optimize the space? The thing was that you made it to O of k square. Can you optimize much more further? The question is maybe, maybe not. Why? Because if you look very closely, that you realize one thing for sure, that for any specific current remainder, if I'm trying to choose any previous remainder, I can only choose that specific previous remainder whose previous is the same as that of current remainder. So I will have to maintain my current remainder and my previous remainder pair. I have to maintain that. I will have to maintain that. I cannot just go and transform and I erased. Okay, I cannot go and just transformly say that okay, my dp of again. I cannot just say directly erase this. Okay, erase the dp of previous remainder. Erase the dp of previous remainder. Erase the dp of previous remainder. I cannot erase it again. By this fashion, it seems okay. Rn dp of current remainder. I am maximizing the answer. It can be dp of current remainder and 1 plus dp of previous remainder. But 1 plus dp of previous remainder, what previous remainder? What? That previous remainder whose previous is same as that of my current remainder. So because of this case, I was in, like, I had to choose a space of O of k square. Now, if you look at the maqsad, the entire aim, the problem was just saying that I have to make my modulo same. Now, when I say same, it could be some specific modulo, which is this modulo. It can be this specific modulo. If that is the case, which means I know one thing for sure, that the final remainder for me, let's imagine, is this specific modulo. Again, this also can be from 0 to k. That's one thing, but imagine it is something. Let's say it is 4. The final modulo, let's say, is 4. Although in the case when it is 2, it is not 4, but yeah, let's say it is 4. Final modulo, it's, let's say, 4. In that case, if you know the final modulo, the issue which you were getting was, for a current remainder, you had to go and try for all the previous remainders, right? Okay. But now I'm saying, I will go and tell you, you can try for all these final modulos, which means you are standing at the index I, you know the current remainder, you're trying for all the final modulos. So with this formula, you can just simply go and find out what your previous remainder should be. It's a fixed one value. So you will say mod minus current remainder mod k. Again, when you do a minus in modulo terms, so you have to add a plus k, then do a mod k. So I just did again. For the folks who don't know, just look at this example, that when your mod could have been a 0, when the mod, like the k value would have been a 4. So previous remainder plus the current remainder mod 4 is actually equal to 0 mod 4, right? But if you do a 0 minus 3 mod 4, that will not give you a correct value. So you have to do a plus 4, then it will give you a 1 mod 4, which is 1. Thus you realize, okay, this is how modulo work. And thus the best part about this is that now your previous remainder is fixed, which will help you in saying that right now, if you are at the current index I, your current remainder is nums of I mod k. Your previous remainder will become mod minus current remainder plus k mod k. Again, as you can see, the same formula. This is the previous remainder, which is now dependent upon current remainder and mod, and both I have fixed now. So my code can easily now become, for a specific mod, value which I have fixed, dp of current remainder can be dp of current remainder plus, or 1 plus dp of previous remainder, because now the dp of previous remainder is fixed as, again, it is fixed as that of the condition. It is fixed, again, it is fixed by this formula, and this formula is fixed as that of the condition that my result should be equal to mod, and I'm adding with my previous remainder. But Aryan, how will you make sure that his previous, again, dp of previous, his previous is actually your current remainder? Bro, that's the reason I told you that this thing entirely, if I go back, this thing entirely made sure that it is following that pattern. It is following that pattern. It is following that pattern. Cool. That is the reason. Now you will not be needing to worry about what the previous remainder of this previous remainder is. It will always be valid because you have derived it from your mod and your current remainder. And mod is actually what is, you will try for all the possible values of mod in K. Now the code is exact same. You will try for all possible values of mod. Then for every possible value of mod, you will simply go and simply try for all the indexes. This will give you the current remainder. You will find the previous remainder for that current remainder. Then you will simply say that dp of current remainder, maximizing your answer, plus 1 plus dp of your previous remainder, and then ultimately getting your maximizing your answer and ultimately returning your answer. With this, your time is still O of n into k. That's still same. O of k into n. The time is still O of n into k, but now the space is optimized to O of k itself. Cool. I hope you guys got it. If yes, then do smash the like, baby, and see you guys at 9 PM today, live stream. Do join Discord and LinkedIn and Telegram to I guess. If not, then do join it. And see you guys. Bye-bye. Take care. I hope you guys got it. It's actually a very good problem and very not easy, not at all medium. It's a medium hard problem. Bye-bye. Take care.